Yeah, good. Okay.
Recording in progress.
Very good. So welcome everyone to this Monday webinar. And today we have a very special guest, José Amigo from the University of the Basque Country in Spain, who happens to have also worked here at University of Copenhagen for quite a long time. So we have had and still have a lot of collaboration. And we're looking very much forward to hear about classical least squares, Jose. So go ahead.
Yeah, okay, Rasmus, thank you very much for giving me this opportunity. And it's always a pleasure to talk to you, to talk to the people there, to the gang there in Denmark, and also with all the participants. And actually, the topic that I'm gonna put on the table today is actually a very nice one. That it's very simple, you will see. But it's a kind of rediscovering things for me in a certain way of doing chemometrics. Okay, so I call it classical least squares.
One thing, did you change your microphone just now? Suddenly, when the recording started?
No,
it's okay, but it's not super. It's
yeah,
okay.
It's my microphone that is a disaster.
That's okay. Go continue.
Okay, so I entitled classical least squares and its variance an extremely useful bunch of tools that should be rescued. I mean, not rescued, but sometimes we tend to forget these beautiful techniques, and we are more focused on other techniques. So indeed, the motivation for me is that, as Rasmus said, I worked a lot of years there in Denmark, but I came back to Basque Country, to my origins here, and here we have several research topics that one of them is actually finding ultra traces of micro and nanoplastics in different types of matrices. One of them is sediments, the other one is filtered water, or we have also some biological samples, okay? And the second motivation is that we have very, so to say, difficult data that we have to kind of classify. And we are actually using some nice filters. Yeah, it's okay.
Yeah.
Okay. So actually, I wanted to talk about these two topics, but I decided to focus only on one because I want also not to be very kind of giving you a lot of information. I mean, it could be a nice topic for discussion. Okay, what I have to say. So let's start from the real motivation that you all know that nowadays micro and nanoplastics it happens that to be all around and everybody wants to analyze them because environmentally speaking, they are a problem, okay? Microplastics because we can swallow them and they can stay there and they can degrade to nanoplastics, and nanoplastics because they can even cross, still to be fully demonstrated, but they can even cross the stomach walls and be part of some cellular tissues. This is not really demonstrated yet, but it might happen. Okay, so here we have a project in which we have to analyze the microplastics of the beach sand. Okay. And I don't know if you know a little bit about how this is normally done in the lab, but for you to have an idea, is you grab some sand, 1 square meter of sand at 2 centimeters thick, then you put it into water, and by flotation, the microplastics goes up, supposedly. Then you take those supernatant, and then you have to filter it in here, and then it comes the analytical part. The analytical part that can be turbogravimetric analysis or pyrolysis, gas chromatography, mass spectrometry, that they are kind of destructive. Or then they come the microscopy, Fourier, middle infrared, Raman imaging, etc., etc. Okay, so actually these techniques and also the procedure to arrive to those techniques, it's very time consuming. So we thought that maybe near infrared could be a nice method in order to find directly the microplastics. Also, it happens that we saw some manuscripts in the literature that actually it seems that it works to find these microplastics in sand. Okay, so we decided to give a try with near infrared. With the cameras that we have here, we could get hyperspectral images. Okay, It's much faster than Raman or FTIR. It's still non-destructive. To some extent, it's cheaper. And we can scan wider sample areas. The limitations, well, the old limitations of near-infrared signals is not that specific. And the spatial and spectral resolution that we have in the cameras here in our laboratory is not that good as from an of FTIR microscopes that we also have here. Okay, so we decided to do the following. We wanted to test. We wanted to see to which extent we could actually quantify very little amount of plastics in sand. Okay, so we took actually sand from the beach and we kind of standardized them in the sense, standardized it in the sense that we submitted the sand to the oven for, I think it's 24 hours, 400 degrees, in order to remove all symbol of organic matter in the sand. So at the end, we only have the sand, this inorganic matter, carbonates, silicates, and all this stuff. And we decided to do something that help us to understand if we are able to find those microplastics, okay? In the laboratory, we have these two cameras available. And here you can see the different Petri dishes where we put the sand. And we also have some plastics, standard plastics. So what we did is to take these plastics as standards, but what we did is to take these pellets and hand carve them in order to obtain microparticles. So we were able to use the Raman microscope to take a picture of the microparticles so we can really assess the size of the microparticle and also the chemical composition of the microparticle. That is, we can take this Raman spectrum and compare to the Raman spectrum of the plastic. Okay. So then once we took that picture with the Raman, we took it, we put it more or less in the center of the sand, okay, and then we scan it with this hyperspectral camera. We did it with many plastics and we did it with many different configurations. I don't want to show you all the results here because probably it would be too many results and we could lose a little bit the focus of this presentation, okay? But I can tell you that we measured it with this camera. That is a camera that measures in the SWIR region. That means from 900 to 200, 500 nanometers with a really nice spatial resolution and spectral resolution, okay? So you got what I did, okay, well, what we did. We carve the microparticle, we create the microparticle and we put it on the sand, on the top of the sand. Then we scan. And of course, as a chemometrician, I thought, that has to be easy. I mean, sand is a very complicated matrix because it's not homogeneous at all. I mean, sand can be whatever, but still, we have plastic. And plastic has a really nice spectrum. So it should be somehow easy. So this is the area that we analyzed. Here we have the microparticle. And we know because we put it manually. Okay, that was really difficult, believe me. Okay. And this is actually the spectrum of the plastic that we are aiming for. In this case, it's ABS. That is a complex plastic because it's formed actually by 3 different polymers. This is actually the spectra we obtained from the pellet, the standard pellet. Okay. And this is some of the spectra we have in the sand. Okay. Sand mostly focused or mostly composed by silicates, carbonates, especially carbonates. Here the sand is full of pieces of shells, so it's mostly carbonate. Okay. So as I told you as chemometrician, I thought that that should be a piece of cake. Okay, so I did a PCA just for the sake of fun, and I saw well, first principal component happens here, and it's quite complicated. Second principal component, third principal component. Here we are. You see this little red dot here. Okay, this is the score surface of the third principal component. And if we check in the loading is the black profile, actually. This black profile has nothing to do, very little to do with the spectrum of the plastic. That is the red profile. And actually, it makes somehow sense that says, okay, what we are detecting in this principal component, it's interpretation. So we thought, okay, maybe if we display the spectra that we have from those small cluster of pixels, yeah. I cannot hear you.
Sorry, you did something so the sound got very low, so people have problems hearing. Before it was much better.
Yeah, every time I touch the screen, the sound goes down and up and down. So be patient with that. Sorry.
Okay.
That's the better I can do. Is the sound card of my computer is not working properly.
Yeah. Okay.
But it's still. I mean, you still understand it, right?
Yeah, I do. Some people say it's not possible actually. Maybe you can change. There's something called original sound. Do you see that at the top?
Okay. See?
Can you click that and make it on instead of off?
Can you hear me now?
Yes, much better.
Much better?
Yes.
Yeah. Okay.
Yeah.
So let's keep it this way. Let's see. Okay.
Yeah.
So coming back to what I was saying, on those pixels here, I could see that there is some signal belonging to the plastic. Okay. So actually, I was really happy, and I thought, okay, if we want to establish a model of a classification model, the most sensible thing to act, or the most sensible way to start, is to consider a single class modeling. That is, we know that plastics are very standard spectra somehow, but what we don't know is what is the spectra of sand. Actually, it's very complicated of knowing the spectra of sand, because sand is completely different stuff every time. So we thought about SIMCA. With SIMCA, we developed some models. Actually, here you have in SMV and first derivative. I mean, the models were pretty cool, okay, but it's normal because the spectra that we use for plastic were kind of standard plastic. That's actually the way we normally do it. But the problem is that the results were not that good. So in the screen in the top, you have the results for SMV, and in the bottom, you have the results for first derivative, okay? Here we have the most probable class being black, the plastic, and white, the sand. So you can see that we have a lot of false positives, because we know that there is only one plastic because we put it there, okay? So there are a lot of false positives. Actually, we check about the probability of having pixels being plastic, it's actually 0, okay? So I was really surprised. I didn't really expect these results because we thought that it could be much easier to find the plastics. Then here in first derivative, we didn't even succeed. So we thought, okay, let's do something that probably is not really okay. That is, let's see with a PLSDA model, this works. So what we did is to take the plastics as one class. And what do we take as sand? Well, sand, we can take one of the parts of the hyperspectral image to have that space explaining sand, and this as a class, okay? It's not really kind of correct, but maybe it helps to understand what's going on with the plastic, okay? So we did PLSDA models, and of course they were, again, really good classification models, but the results were like this. What you have in the top, it's with SMV, what you have in the bottom is first derivative. In black here, you have the plastic, in white, the sand. As you can see, we didn't find the plastic. Now with the probability for being plastic, we can really see a dot here in white as probability, but look at the dimension, look at the number here, is 10 to the power of minus 116. I don't even know if this is possible, actually. That probably is a computational error, or, you know, this type of things, because this number is completely, I mean, it's 0, okay? So the results from PLSDA were not actually really good, and I was really surprised. So SIMCA did not really work. PLSDA did not really work. And before you ask me, I tried many other things: support vector machines, feedforward backpropagation, neural networks, multivariate curve resolution with different constraints, and spectral angle mapping. That is a technique that in remote sensing the people use quite a lot, and they didn't really work well. So it happens that some years ago, a couple of years ago, we published this book, Hyperspectral Imaging, and I asked this guy here, Neil Gallagher, from Eigenvector, to write a manuscript or a book chapter about classical least squares, because I think it's a nice way of studying hyperspectral images, and I know that he particularly likes these methods. Okay, so I remember that in this book chapter, he talked not only about classical least squares, but also something called anomaly detection. Okay, so actually, he was talking a lot about decluttering methods. The decluttering methods are methods in which you have a target and you know which target you have. So as long as you point that target, the rest can be considered what is called clutter. Clutter means noise, means signal that has nothing to do with what you are looking for, okay? The concept is well common in radars, okay, radar detection. And actually, to suppress clutter from signals, you need only two things. Your signal, that means your hyperspectral image, and the target that you want to localize. In this case, this is our situation because we wanted to localize one microplastic, okay? So let's start with one microplastic. So actually, we also I also read in that book chapter that classical least squares can be weighted with different strategies in order to downweight the variance that has nothing to do with your signal and increase the variance that has to do something with your signal, with the target that you are looking for. Okay, so putting a little bit of equations here, we all know, I mean, I will assume that we all know classical least squares. That is a very well-known strategy. So actually, when we do classical least squares, what we want to do is to minimize the error, okay, this equation here. And the trick here is this weighting matrix, okay? Indeed, in the manuscript, Neil explains that the general approach to solve the problem, sorry, a little bit of Spanish here, to solve the problem is to calculate this weighting matrix, considering what's your target, what you are looking for, in such a way that if you calculate a CLS model with this weighting matrix, and here we are, and you can assume that your spectra, the spectra that you have, that you are looking for, are the spectra that you are calculated. Your weighting matrix is just one. It's just a scalar number. Okay, this is the classical situation for classical least square solution. But this condition is only fulfilled if your spectra behaves perfectly linear. Okay, and you perfectly know everything you have in your matrix, in your sample. And in this case, that's absolutely impossible. We know that we have plastic, but we don't know what we have in the sand. It can be whatever thing, okay? So then I read in this book chapter what is called also the Aitken estimator, the generalized least square estimator. So actually, in the GLS solution, what we can do is to construct this matrix, this weighting matrix, considering that in the space spanned by your data, there is a subspace that is focused on, let's call it noise, rabbit signal that you don't want, and it still remain a space in which you will have the signal you are looking for, okay? So this weighting matrix is calculated like this, like removing all the mean average variance of your data, and then calculating the classical least square model with this weighting matrix. Okay. There is also another variation that we will talk later in the second example that I will show you, in which this matrix is just calculated by using one of the best methods that we have in chemometrics, that is PCA. PCA is especially good at calculating the highest sources of variance in your data in the first principal components. So you can calculate that PCA model and use the loadings of that PCA model in order to remove that information from your matrix, and then use that weighting matrix in order to calculate that concentration. That is the concentration of the signal that you are looking for. So actually, I decided, well, maybe that could be a solution. I program some functions in Matlab, and as I say, are you ready here? Because when I apply GLS in like this, I obtain this. I mean, I thought that I was wrong, that my coding was wrong or something, because it's quite normal that my coding is wrong. But no, apparently it was okay. And suddenly in less than 1 second, I obtained this solution. Looking close at this solution, okay, what we obtained here is the microparticle, okay, but also a bunch of spectra. And for following the next rationale, I keep the colors. The problem here is that this parameter is not really well understood. I don't know what this number means. Okay, so 0, or in this case 0 because I normalized the result, 0 means that has nothing to do with the target I'm looking for. 1 means it has a lot of things to do with the target I'm looking for. So I kept the color here. And as you can see, the most reddish pixels, the spectra here, they really resemble a little bit more with the target I'm looking for, while the bluish part resembles nothing to the target I'm looking for. Okay, and once I localized this microparticle, I thought, okay, maybe now I can understand a little bit more why the other type of model, classification models, don't really work well in this situation. My macroparticle is very small. It's around 800 microns in the largest dimension. And we put it in sand. That is kind of a refractant matter. So what we have here is actually a perfect mixture, not only of pixels belonging to plastic, but also in those pixels, we can see a lot of signal of the sand. So basically, when I construct my classes in the classification models, I am not considering the fact that the pixels I'm looking for, or the spectra I'm looking for in my matrix, are not the ones contained in my classes in the classification model. That's why classification models don't really work well. In this case, GLS worked well because still we have some part of the signal that belongs to the plastic. Okay, so I wanted to dig more about this, and I came back not to the same manuscript, but to another one that is here we are. This one, net analyzed signal calculation for multivariate calibration. Okay, so I'm pretty sure that you are familiar with the net analyzed signal concept, but I can explain you roughly. Yeah, okay. Imagine that we have our variable space, and this is our reference. Okay, so any spectra here, can you hear me fine, Rasmus? Yeah?
Yes, all good.
Okay, okay, so any spectra will be here. Okay, so the net analyzed signal, one of the net analyzed signal concepts focused on classical least squares, it says that it's easy to calculate the projection, how much of my spectra belongs to the reference, that is this one, and how much of my spectra has nothing to do with my reference, that is the orthogonal part. So I can calculate the projection of my spectra to the reference, and I can calculate the orthogonal part. And it happens that if I normalize these two fellas, indeed what I have is in my space that is normalized. Okay, I imagine that this is a circle centered in zero. Okay, so if this is my reference, and this is the spectra that I want to compare with my reference, the closer my spectra is to the reference, the norm of the projection will be closer to 1 because everything is normalized, okay? Of course, this is classical least squares. This is only one reference spectrum, so we have to trust in that reference spectrum, but not as a kind of quantitative point of view, but as a qualitative point of view. Doing this thing, I calculated the project of this little part where I have the microplastic. I calculated the projected on the projected part and the orthogonal. I calculated the Pearson correlation coefficient of the projected part of my spectra to the reference. And of course, there are only two results that can be obtained, +1, -1. If you have +1, it means that you have certain amount of correlation. If you have -1, it means that it's pointing through the other direction, okay? And then from here, I can calculate the norm of the projection on the reference spectra. And here, I obtained a map that tells me how much of the spectral signal of that particular pixels might belong to the plastic. And that's a really nice indication. But as everything in this world in chemometrics, there is something to be considered. There are many things to be considered, but one of the main ones that is this thing strongly depends on the spectral information you are given. For instance, what happens if I, instead of comparing everything, I compare only one wavelength range? Like for instance, from 1,500 to 2,200. The result here, it gets, let's say, nicer. But what happens if I take the other part? From 900 to 1,450 nanometers. The result is a disaster. What basically is telling me that in that wavelength region, my spectra has no information whatsoever with the plastic. And that's fine, because if we look at this plot here, in this region, it's very difficult to find signals of the microplastic in the real sample. So it actually makes sense, okay? So this is the first case that I wanted to comment with you. We are still working. Of course, we have many samples, and there are many questions to be asked here that I will put at the end, because maybe we can check them actually. But I wanted to show you another example in which GLS might be extremely useful. It's the thing that we are also having some problems with some companies that they have microplastics in some water streams of their manufacturing processes, okay? So they know that they have polyethylene terephthalate, and they wanted to find polyethylene terephthalate microplastics in water. In this case, the particles are extremely small. They are smaller than 200 microns, okay? So indeed, in this case, we use Raman imaging that we have in our facilities. So what we did, here we are, what we did is to take several liters of water to filter out through this aluminum filter, and then to scan with Raman imaging. Of course, this is very tedious and very time consuming, but the spectral resolution and the spatial resolution is the one we need in this case, because the microparticles are extremely small, okay? We were also said that we could have between, around 50, 20 microparticles in other studies that they made with the other techniques, that they could be between 50, 20 microparticles in there, okay? So after we scanned with Raman, again, I thought that this could be an apparently easy thing. I mean, we are scanning in Raman in a neutral filter, and we are looking for polyethylene terephthalate that, by the way, it has a really nice spectrum in Raman with this laser, okay, and these conditions. So actually, I mean, again, I thought that this could be, you know, piece of cake somehow. Okay, so I checked what happens with a PCA, and then I tried to think about, okay, what happens if instead of using classification stuff, I use checking in libraries, okay? And in libraries, there are two methods. There are standard kind of methods. There is a spectral angle mapping is one of them. Then there are many other correlation stuff, but I also wanted to try GLS and ELS, okay? So actually, this is the data, okay? This is the false RGB image. That basically, it shows me a kind of quick vision of what I have in my sample. And when I saw this one, actually, my mind, you know, mind always play tricks on you. So you think, oh, you have here the microparticles, okay? That's beautiful. But actually, I made PCA on this image. And I tried to cluster the data into 10 clusters. And here you have the 10 clusters. The black spectrum you have here is the reference spectrum. So it was not found by PCA. We don't have this. I put it here just to compare the signals we have in our samples, in our sample, with what we are looking for, what we are aiming for, okay? So the first thing I saw is that we have signals with very, very low intensity, okay? Here we have microparticles, but the spectral intensity is very low. Then we have a strong and very heterogeneous fluorescence effect. So we have this fluorescence in here, but we also have this fluorescence in here, and we have also many other types of fluorescence. Then, of course, we have a spectra with many satiated values. And there is a problem here. Satiated values at one point in the spectra doesn't mean that here you might not have a signal belonging to the plastic, like in this case, for instance, okay? And actually, one of the things that I was really pissed is that I couldn't see any trace of PET, okay? So indeed, I mean, I kind of expected this result. So then it comes the part of the library. But there is a thing. This data is crazy, so we have to pre-process this data somehow, okay? And one of the things that you can pre-process is with derivatives. That's fine, it works. There is also something called baseline correction with weighted least squares, okay? That I will show you here. But weighted least squares is a problem because it needs to be optimized for every single case you have in your hyperspectral image. And in this case, we don't have a baseline that behaves always the same. We have like 20, 30 different types of baselines. So actually, I wanted to really skip pre-processing as much as possible, okay? Because this is what happens when you apply weighted least squares that has been optimized only for your reference, indeed, okay? So this is the optimization for the reference. And this is what happens when you apply this to the rest of the pixels, the spectra of the pixel, that actually all these small peaks become, that is noise becomes very weird and stupid peaks. So we were not really interested in that. So we thought about the spectral angle mapping, that is basically the cosine of the angle between the reference and the rest of the pixels in my, the rest of the spectrum in my image. This is a technique, this is a method that is very used in areas like remote sensing, for instance. So I thought it could be a nice alternative. Then I also thought about correlation coefficients, normal correlation coefficients that, as you know, calculates or compares covariance with variances. So maybe that would be a nice alternative. And of course, I thought about generalized least squares and extended least squares, the exact same strategy that you saw before, okay? So what happens with the spectral angle mapper or the mapping, the SAM strategy, it actually didn't work well because I did it on raw data. I remember that I really wanted to skip the pre-processing part because it was hell in this type of images. So it didn't really work well. It didn't find, I mean, it found two to three spectra that, or pixels that contain microplastic, okay, the PET signal. What I did here is the following. I applied the technique, spectral angle mapping, then I established a threshold on the value of the cosine of the angle, and then I select the pixels that are above that threshold, and from that, what I do is PCA, that is much easier, and then I check the spectra I found to be kind of candidates to be microplastic. And in this case, it didn't solve the problem, as you can see here, okay? Then with correlation coefficients, it was even worse, okay? It was kind of annoying. But my surprise, again, came when I applied generalized least square. The same strategy as before. This is the result. This is real data, it's not simulations or whatever. So I found some targets, then I made PCA, and I kind of filter out. And I found that in this particular sample, I have 35 pixels that contains microplastics. And that was beautiful, actually. I mean, I found this spectra just with this alternative, and it works. And what happened with extended least squares, the one that makes PCA before and kind of deflates or calculates the weighted matrix with the loadings of that PCA model? It actually gave the same result. So I was actually really happy because we have a simple methodology that was able to find this type of ultra traces in my samples. Indeed, I was really impressed because some of the pixels that I found had very, very little signal compared to the standard signal that we were using. And that was something really nice for solving the problem here. Okay. So indeed, as I said, I wanted to show you this thing that sometimes this kind of more simple alternatives are quite useful to solve issues in this type of samples. But of course, we have to talk about when these things are actually really useful. Because one of the things that I always said to all my students is that our solutions are very local sometimes. So you can globalize a solution, but what I'm proposing is a very local solution, okay? So the first thing that we have to investigate is what happens, for instance, if we have more microplastics, that is, what happens if the concentration there increases, okay? Also, what happens when we have a scattering that from the particle goes to the neighbors, or the scattering that goes from the neighbors to the sample? So how can we handle these situations? This is what concerns to the spatial effect, okay? Or what happens if we have a particle that is between these 4 pixels? What's gonna happen with that signal? Because I will have a mixed signal in these 4 pixels. So if I find it, maybe I think that this particle is 4 pixels big, but it's only 1 pixel. Okay, or what happens if we have these situations, or even this situation in which we have a mixture, okay? Concerning the spectral resolution, of course, this technique depends on the spectral resolution of my microplastic and with what we are comparing the microplastics. In this case, in the Raman case, it was kind of neutral thing. In the sand case, it was a kind of irreproducible signal, okay? And also, what happens with the method? Okay, generalized least square is really nice, but questions that I have and that we are now checking, what happens, what is the limit of concentration where GLS can work fine? That is, what happens if we have 20% of our sample that contains microplastics? Will it work? Probably not, because as we said, it's meant to find very small amounts of things in images, okay, or in data sets. What happens if we have, instead of 1 microparticle, what happens if we have more microparticles, or what happens if we have microparticles of different plastics? Because we normally have mixtures. I mean, we not only have PET or ABS, we have a mixture there. So will it work fine? Well, I can tell you that, yeah, it works pretty nice, but I didn't have time to put those results here, but it's something that is worth to study. What happens with the same plastic, but if the composite, the formulation of the plastic is different? You know that we have PET, normal PET, but we also can have PET with brominate flame retardants or with a colorant or with something like that, okay? And that's something very important, is to which extent the limit of detection that I talked before, this net analyzed signal, can really be ascribed to a single spectrum that we use as reference. That's also a big problem, that we rely on that reference. Okay, we are relying all the time to that reference. So maybe that reference might not be that good. Okay, so as you can see, there are really pros and cons in this methodology. Okay, I'm not claiming that is the one you have to use, but I always say, but like everything in spectroscopy and chemometrics, we aim at finding the best local solution that solves our problems, considering, in this case, the spectral interferences, the spectral quality, the spatial quality, the availability of the database that we have, also the quality of the data in the database. In this case, it's especially dangerous because we cannot have this kind of standardized sand. That's something that doesn't exist. We don't really know how many components we have in the sand, so-called sand, okay? So that's something that we have to check. And also about the performance of the algorithms. It doesn't mean that since in this case, classification methods didn't work and GLS will work, we have to focus and use those ones. No, no. What I say is that one of the things that I always said as well is that we have methodologies there and in the background that they are extremely useful and they are simple, very simple. In this case, GLS, trust me, is really simple, conceptually speaking and programmatically speaking. It's very simple to apply. And in this case, it gave us a lot of information of what happens to the spectral quality and what happens to our microparticles. So actually, this is an example in which we should not forget that in this thing that the chemometricians, I like to be more chemo than metrician. And I really like these methods because with simple information can give us simple, nice results. That maybe they are not the quantitative spectacular results, but they can give us a hint of what's going on with information in our samples. And I think that's all.
Perfect. Thank you so much, Jose. So if anyone has questions, feel free to actually either write them or ask them. But I can start out by saying, have you played, I mean, I know that when Neil uses GLS, he uses a lot of different ways of defining the weights, like samples with similar Y values being downweighted, the difference in the spectra of similar response and stuff like that. Have you played around with those things?
Yes, yes, we are playing a little bit around with more combinations of how to create this double view matrix. The one that I show you is the simplest one, but when the things get funnier, like for instance, you have 3 different types of microparticles in your sample. If you want to avoid to have false positives, false negatives, and all this stuff, you really have to play a little bit more with double view matrix. And exactly what you said. I mean, when you in the Y, certain values you establish a threshold, so certain values are declared as clutter or not clutter. So yes, we are. I mean, this is something that it's nice, it's promising, but we are still working on that.
Right. But that you can be very creative, right, with how you create. Yes.
Yeah, that's why I wanted to show the simplest, the straightforward way that we are using, and actually it's working also because we have a very particular problem. In this case of the PET, it's a very particular. There is a company that has this problem, so it works. It simply works.
Right. Oh, and we have the man himself here.
Whoa! I put a picture of you. You saw it?
So saying hola, which is nice. Yeah, okay, so when does it really break down? when is it not a smart thing to do you think?
Yes, look at this. I can show you, but first I have to find it. Let me see. The book.
You were saying when the clutter isn't correlated.
Exactly. Let me show you. Okay. Here we are.
And since Neil is here, I can also say that, of course, you can do this in PLS Toolbox, which Neil is a part of. Is it possible to do in your software, Jose?
In HyperTools, yes. Not yet. I mean, give me a break, man. I have.
But it will be.
It will be soon, very soon, actually. Let me show you this, because that question is very interesting. So we are actually doing some simulations in which we change different parameters. I want just to show you some. It really breaks when the concentration of the the concentration of the target in your sample starts to be large enough. That is what the clutter isn't correlated. It means that with the downweighting process, you are actually removing part of the target you are looking for.
Yes, makes sense. So in this particular way you're using it, it has to be a small signal, and it has to be have a different spectral shape, so to speak.
Yeah.
That makes sense. Okay, very good. Any other questions? Otherwise, I'm sure that you can always mail Jose.
Are you not fan preprocessing because it's a specific solution, because it's hard to optimize? Oh, no, I'm really fan. I am go for preprocessing. No, the message was that optimizing the preprocessing in the Raman hyperspectral image was hell, because we have so many different artifacts that we really wanted to skip it, because otherwise you cannot optimize for all the hyperspectral image. You really have to go little by little, optimizing it, the baseline, or finding the parts of the spectra that are kind of. Okay, so it's not that I'm not fan of preprocessing. On the contrary, I really think that a good preprocessing can be really nice. But in this case, we had 300 times 300 pixels, and we have very different artifacts. So I really wanted to. I thought, okay, I don't really want to preprocess this data. So actually it worked without preprocessing. I can tell you that with first derivative, it also worked very nicely. Okay, but yeah, in this case, without preprocessing, it also worked very well. But no, I completely agree that a good preprocessing method, well done, it's always good.
And Sergey, you have a question?
Yes, first of all, thanks, Jose, very interesting. As far as I understood, this works best when you have a target spectrum, right? When you have a pure spectrum of the target. But what if you don't have one, but for example, you have two images? You know, for example, that on one image, the concentration of this target is particularly high, but you have no idea where the target is, so it's a mixture. And on the other image, you know that the concentration is very low. Can you construct this model based on these two images then?
Yes, and you have to check the book chapter by Neil, because I think he has an example in which he actually says that, and actually he shows that, in which there is not a target spectrum per se, but doing some analysis, you realize that there is something there that could be considered as target spectrum. And actually the example that is in the book chapter is really nice.
Okay, thanks. So I have something to read then.
Very good.
Good.
Okay. Any other questions? Yeah, I can also say that we're going to put this on YouTube, so you need to re-see this. There should be opportunity for that.
I have one more, if you don't mind.
Perfect.
You mentioned something that is you told like weighted least square correction of baseline in case of Raman spectra. Is it this asymmetric least square, the perfect smoother, or it's a different one?
Yeah, it's the weighted least squares is something similar to asymmetric least squares, but I'm not exactly certain about what is the difference. Actually, if you know, guys, I'm not pretty certain of what is the exact difference. I think it's something very similar. But really, in our images, I know that in the small Raman images, and when the baseline is kind of, the baseline drift due to the fluorescence is kind of similar to all the pixels. It's really handy, it's really nice. But in our images, it's something close to hell, because you have so many different baselines and so many artifacts that, if you have to optimize that for every single one of the pixels, is no way.
Okay. Yeah. Thanks.
Okay, I look forward to having it in your software, Jose. That's going to be nice.
Yeah. Give me some time, please.
Yeah, it's fine. It's 5 o'clock here.
6 is fine?
Yeah, that's perfect. No problem.
Okay.
Okay, thank you very much, Jose, for this. This was very interesting.
Okay, no, thank you, actually. And well, if you, I know many of you, if you have more questions, concerns, even a really nice criticism, because this is an ongoing work, just please send me an email and we can just talk about this.
Perfect. Have a nice Monday.
So I should stop recording.